Hello everyone, and welcome to today's afternoon session. Our first speaker for today is Dimitrios Ntalampekos from Stony Brook University, and he's going to talk about the definitions of quasiconformality and exceptional sets. Please, Dimitri.
Hello everyone. I'd like to thank the organizers for giving me this opportunity to talk about my research. So my talk will consist of two parts. The first would be to describe the classical definitions of quasiconformality and then some new definitions or some new definition. And in the second part, I'll talk about the exceptional or else removable sets for quasiconformality. So let's first start with the classical definitions. We have an open set in Euclidean space. You can think of the plane if you prefer. And we consider an orientation preserving topological embedding, a homeomorphism. So according to the classical analytic definition, F is quasi-conformal if first F lies in the Sobolev space, W1n, and second, we have this distortion inequality. So the differential to the nth power is less than k times the Jacobian almost everywhere. So this is much easier to understand with a picture. So the distortion inequality just says that if you take a ball, a geometric ball, then the differential, which is a linear map, maps this ball to an ellipse, if we are in dimension 2. And the eccentricity of the ellipse, which is the ratio of the major to the minor axis, is bounded by k. Now, this condition is required to hold almost everywhere. Okay. However, the distortion inequality just by itself does not give quasi-conformality. So it is very important that we also have this regularity. Okay. So again, it's not sufficient to require that almost everywhere we have this picture. Now, let's see another classical definition of quasi-conformality, which is equivalent to this one. So this is the so-called metric definition. Now, according to the metric definition, we first have to introduce some notions. So let me just explain these notions by the picture. We take a ball centered at x of radius r, and we take the image of the ball. So the image is going to be some topological ball because F is a homeomorphism. And then we take the largest ball that is contained in the image and has center f of x. So the radius is going to be this number, little lf. Then we also take the smallest ball that's again centered at f of x and contains the image. So the radius here is going to be the capital LF. And then we take the ratio of these two numbers. So the ratio somehow gives us the eccentricity of the image of the ball. Okay. So if the ratio is close to 1, then this means that the image is close to being a round ball. Okay. So according to the metric definition of quasi-conformality, which is due to Gehring from the 60s, F is quasi-conformal if and only if the limit of the eccentricity at r goes to 0 is uniformly bounded for every x. Okay. So again, what does this mean? It means that, well, if you take balls shrinking at the point x, then the images should have some kind of bounded shape. They should have bounded eccentricity. Okay. So they should not be very squeezed. Now, this is the metric definition of quasi-conformality. As you can see, it can be defined in a more elementary way. It doesn't require Sobolev spaces or differentials or Jacobians. So it's defined only using the metric, the Euclidean metric, and that's why it's called the metric definition. Now, let's go to the next step. Let's see a slight generalization of this definition. So 35 years later, Heinonen and Koskela just proved that you can replace lim sup with lim inf. Everything else is the same. Okay, so this is the only change. But this was actually a significant improvement. So this definition says that, well, you don't really have to check quasi-conformality at every scale, but only at a sequence of scales. So all you have to do is check that if you take a sequence of balls shrinking to the point X, then the images have a kind of bounded shape. Now, this theorem found many applications in rigidity problems in complex dynamics. So here I just cite some works. And what do we mean by rigidity problem? I mean, one of the big open problems in dynamics is, in general, to understand when we can upgrade the topological conjugacy between dynamical systems to a quasi-conformal conjugacy. And this type of result is very helpful in this direction. Why? Because in dynamics, a lot of times we don't have information or control over all scales or over all iterates of a function, but we only have information about a sequence of scales or a sequence of iterates. So it is very important that we don't really have to check every scale. Now, a natural question that arises from this definition of quasi-conformality is whether we can make it more symmetric. So this definition, again, requires that balls get mapped to bounded shapes. But the question is, can we make it more symmetric and instead require that sets of bounded eccentricity are getting mapped to sets of bounded eccentricity? So we want to have a picture like this. And this is also desirable in complex dynamics because a lot of times we don't know what the image of a ball looks like, but we might have more information about puzzle pieces, for example. We might know what is the image of a puzzle piece, but we don't know what is the image of a ball. Okay, so let me give some definitions before moving forward. So if we're given a bounded open set, we can define the eccentricity of that set. So E of A is the eccentricity of A. And how do we define it? Well, we take concentric balls. One is contained in the set, the other contains the set, and we want to minimize the ratio of the radii. Okay, so here essentially there are two infima, one over all the possible centers, so we are allowed to freely move the balls, and also over the ratio of the radii. Okay, so this is the formal definition of eccentricity of a set. Now, if we're given a homeomorphism, then we can define the so-called eccentric distortion at the point X at scale R. So how is this defined? Well, we take sets A, open sets A that contain the point X and have diameter less than 2R. And then we compute the eccentricity of these sets, of such a set. And we do the same for the image. So we take f of A, that's going to be another open set. It contains f of x, and we compute the eccentricity. So the eccentric distortion will be the smallest value m, so that the eccentricity is bounded by m, both in the domain and the range. Okay. Now, you will notice here that the points x and f of x have nothing to do with the balls. So in the previous metric definition, x was the center of a ball and f of x was the center of the balls. But here, all we require is that x and f of x are just contained in the sets A and f of A. So according to the generalized metric definition, f is quasi-conformal if and only if the limit of this eccentric distortion is uniformly bounded for every x. Okay, and maybe it's easier to describe what happens with words. Equivalently, we require that there exists a sequence of sets, an, that shrink to the point x. So there's a sequence of sets shrinking to the point x, so that the images shrink to f of x. And both sets an and f of an have uniformly bounded eccentricity. Okay, so this is the generalized metric definition that I wanted to present. Now, the proofs get significantly more complicated when you pass to further generality. I mean, the first definition was due to Gehring, then there was the Heynon and Koskela, then we have this theorem. The basis of the argument is I would say it's classical. It's a discrete modulus argument, but the details get more complicated when you have to deal with arbitrary sets of bounded eccentricity rather than geometric balls. So I won't get into any more details. Now I'll move to the second part of the talk, which is the question whether we really have to require these conditions for every x, or whether we can exclude something. Okay, so that's the next question. So do we need to assume that these limits, these eccentricities, are uniformly bounded for all x? So as we discussed in the beginning, we can't really exclude a set of measure 0. That's too large. Okay, so we have to be a bit more restrictive. Now, let me give you the formal definition of an exceptional or a removable set. Of course, you can take this as the formal definition, namely, require that, let's say, EF of x, comma r is uniformly bounded as r goes to 0 for every x except for a set E. But let me give you the definition for closed sets because it's a bit easier. So a closed set is quasi-conformally removable if every homeomorphism from Rn to Rn that is quasi-conformal outside E is actually quasi-conformal everywhere. And again, here, by using different definitions of quasi-conformality, you can give the definition of a removable set even if it's not closed. I just stated for closed sets because you can use any definition of quasi-conformality or conformality here. So pictorially, what happens, suppose that E is this Jordan curve, this simple curve, and we're asking the following question. Suppose that we are given a homeomorphism from the plane to the plane that is conformal inside, that's conformal outside. The question is whether it is also conformal on the curve, on points of the curve. So essentially, it boils down to checking that the derivative f prime of z exists. All right, so this is the definition. Now, let me give you some examples of removable sets, just to have an idea what is removable and what is not removable. So first, all sets of sigma finite Hausdorff n-1 measure are removable. In dimension 2, this simply means that sets of sigma finite length are removable. So for example, all smooth curves, all rectifiable curves are removable. This is due to Besikovich in dimension 2. And then in higher dimensions, there are different proofs based on the definition of quasi-conformality. Then the next class of sets are quasi-circles. So the most famous quasi-circle is the von Koch snowflake, which I'm sure you're familiar with. And roughly speaking, a simple closed curve is a quasi-circle if it has no cusps, right? So this is a cusp, and therefore this curve is not a quasi-circle. Now, let us note that quasi-circles can have Hausdorff dimension arbitrarily close to 2. They cannot be, it cannot be equal to 2, but it can be as close to 2 as you wish. So certainly quasi-circles are not necessarily rectifiable. But conversely, we can have rectifiable sets, rectifiable curves with cusps. Okay, so therefore these two classes of sets are in some sense singular to each other. Now, another class of removable sets includes the boundaries of John and Helder domains. So what are these? These are generalizations of quasi-circles. John domains allow for inward cusps, but not outward cusps. So in what I drew here, the interior is a John domain, the exterior is not John. the interior is a joint domain because it has only one inward cusp. The exterior has an outward cusp, so it's not joint. Now, Hilbert domains are a further generalization of joint domains, which also allow for some outward cusps, but not too many on average. So there is some integral condition that controls the cusps. So again, one could say that these two classes of sets are removable for geometric reasons that have to do with cusps. And finally, another class of removable sets are the NED sets. So these are negligible for extremal distance. They were studied by Alfors and Berling in the 50s. I will say a few more about these sets later. So for the moment, let us point out that we have three different classes of sets. We have the rectifiable sets, we have the sets that are removable for geometric reasons, and we have these NED sets, which one can say that they are removable for potential theoretic reasons. It turns out that all these classes are disjoint. And well, they're not disjoint, but they are singular in the sense that you can find sets lying in one class but not lying in the other. So it looks like we have three different types of sets that imply removability. So the question here is, how can we characterize removable sets? This is a big open problem. And if one wants to resolve this problem, first we have to understand what is the common reason for which these three types of sets are removable. Okay, so let's now talk about NED sets in more detail, this last class of sets. So here we need to introduce modulus. If we have a family of paths in Euclidean space and a non-negative Borel function, then we say that rho is admissible for the family of curves gamma if the line integral of rho over gamma is bigger than or equal to 1 for every rectifiable curve in gamma. And then the modulus of the curve family gamma is defined as the infimum of rho to the n of the integral of rho to the n over all admissible functions. For those who see this for the first time, this definition might seem a bit obscure. A related notion is that of extremal distance, which is simply the reciprocal of modulus, but I prefer to stick to modulus because it's more commonly used in modern quasi-conformal theory. So modulus, we can think of modulus as an outer measure on curves, and actually it is an outer measure. So in some sense, it measures how big a curve family is. So now let's give the definition of NED sets. A closed set is NED if the modulus of the family of curves that joins two continua is the same as the modulus of the family of curves joining the two continua but avoiding the set E. So let me draw a picture to explain this. Suppose that we have two continua and we have a set E in between them. And we're looking at the family of curves that join the continua. Maybe some curves intersect the set E, maybe some curves avoid the set E. So the question that we are asking is whether the modulus of the entire family of curves is the same as the modulus of the subfamily that avoids the set E. If yes, if this is the case for every pair of disjoint continua, then we say that E is removable, is NED, sorry, it's NED. Now, there is a different way to reformulate this definition. So we can define F0 of E to be the family of curves that avoid the set E, except possibly at the endpoints. And then we can rewrite this definition in this form. So we can simply say that the modulus of the family of curves joining the continua is the same as the modulus of the family of curves joining the continua intersect F0 of E. Okay. So as I mentioned before, the NED sets were studied by Alfors and Berling, and they identified their their relation to complex analysis, their precise role in complex analysis. But let me not say much more about these sets. Now we're going to introduce a larger class of sets, a much larger class of sets, the CNED sets. So CNED stands for countably negligible for extremal distance. So we just introduce the word countably. And how do we define this? Well, we define f sigma of E to be the family of curves that intersect the set E at countably many points. And then we give the definition of a CNED set. So a set is CNED if, so we have exactly the same definition as before, but now we have the collection f sigma instead of f0. Right, so again, we take two continua, we take a set E and between them, and we look at the family of curves joining the two continua. So we are asking the question whether the modulus of the entire family of curves remains unchanged when you look at the modulus of the subfamily that intersects the set E at countably many points. Okay, so in this case, we say that a set is CNED. And now the main theorem states that these CNED sets are removable for quasi-conformal maps. Namely, if we require that the eccentric distortion, the limit is bounded, is uniformly bounded outside the set E, then F is quasi-conformal. Of course, the natural question is, what types of sets are included in this new class? Okay, so is it something new? Is it something interesting? So it turns out that all the previous examples that we discussed are included in this class of sets. So the rectifiable sets are included. Let me give you a heuristic reason why this is the case. So let's take a rectifiable curve. And let's take a straight line intersecting this rectifiable curve. So a straight line might intersect the set E at uncountably many points. However, rectifiable sets have the property that if you take parallel translates of the curve, then almost every parallel translate has the property that it intersects the set E at finitely many points. Okay, so this is the property of rectifiable sets. So somehow by slightly perturbing your curves, you can intersect the set E at only finitely many points. And this is actually what implies the CNED property. Now, next, again, quasi-circles and boundaries of John and Helder domains are also included in this new class of CNED sets. The argument here is much more complicated, but the idea is the same. For example, if you have the von Koch snowflake, okay, it's not a very good picture. And if you take a straight line, then it will intersect the von Koch snowflake at the Cantor set. But somehow you need to slightly alter the curve, modify it so that the intersection is countable or finite. And finally, the NED sets are also included, as we mentioned. So the CNED class is much larger than the NED class. Actually, the NED sets are necessarily totally disconnected, but the CNED sets can contain curves. Okay, so far it looks like the CNED sets form a candidate for a characterization of removable sets. And this is actually an open problem that would be very interesting if it was resolved. So what about new examples? Are there any new examples of sets that are included in this new class? So first, there is even a non-measurable set that is CNED. Now, why is this interesting? Well, it says that CNED sets can be very, very complicated. Okay, so that's why we look at such examples. Now, what is this set? This set was constructed by Sierpinski, and it has the following property. it's a set in the plane that has the property that every straight line intersects the set in at most 2 points. Every line. Now, did Sierpinski care about quasi-conformal maps and removable sets at that time? No, but he constructed this example as a counterexample to the converse of Fubini's theorem. So Fubini's theorem says that if you take a measurable set, then almost every slice of a measurable set is also measurable.
Sorry, so can I just check, in your theorem, you do not assume the set to be closed?
Exactly, correct, yes.
Okay, so this removability holds as long as, so you could take this set by Sierpinski and that your theorem would apply to it.
Correct, yes. So if you use the metric definition of quasi-conformality, you don't need to assume that the set is closed.
Okay, thank you.
Okay, so as I was saying, that this set has the property that is a counterexample of the converse of Fubini's theorem. Okay, so it's a set whose slices are measurable. They consist of 0 or 1 or 2 points, but the set itself is not measurable. And also, we can generate a lot of examples by taking unions of CNED sets. So unions of closed CNED sets are also CNED. So we can combine these sets together. Now, I'll talk about unions a bit later. So for the moment, let's also discuss a bit the non-CNED sets. So all sets of positive area are not CNED. This is for trivial reasons, but let me not discuss it further. The first non-trivial examples are the product of a Cantor set with 0, 1, with an interval. So let me just show you, at least at the heuristic level, why these sets are not CNED. If you take a curve that goes through the set, then no matter how you change or you perturb the curve, all the perturbations will still intersect the set at uncountably many points. So there's no way to avoid the set, to avoid having uncountable intersections. And this is the heuristic reason why these sets are not CNED. Now, for the same reason, the Sierpinski carpets are also not CNED. So this is the standard Sierpinski carpet that is constructed by squares, and then any homeomorphic copy of it is called the Sierpinski carpet. So these sets are also not CNED for the same reason as before. If you take the curve that crosses the Sierpinski carpet, then every perturbation of the curve, no matter how you alter the curve nearby, you'll get curves that also intersect the carpet at uncountably many points. So it turns out that carpets are also not removable, but this proof is more involved. So it's much more elementary to show that carpets are not CNED. Of course, non-removable implies non-CNED, but I'm saying that it's more elementary to show the non-CNED property. And finally, the Sierpinski gasket is also not CNED. Again, it's non-removable, so we can argue directly in this way, but it's much more elementary to show that it's not CNED. So let's see how you can show this. Well, if you take a straight line, then a generic straight line will intersect the Sierpinski gasket at an uncountable set, but you can try to modify the line so that the intersection becomes countable. Namely, if you go through these connection points between adjacent triangles, and then you erase these parts of the green line, then we have created a curve that's very close to the original green curve, but it intersects the gasket at finitely many points. So we have these connection points there. So it looks like that maybe the gasket is CNED, right? Because we can alter the curve slightly and go through these connection points to make the intersection countable. However, there are only countably many points that we can use to make these alterations. So the points between adjacent triangles are countably many. And conformal modulus does not really care about the family of curves that goes through a countable set. The modulus of curves going through one point or through countably many points is 0. So the moment we make these alterations and pass through these countable sets of points, we have automatically created a curve family of modulus 0. And therefore, the gasket is not CNED. All right, so these are some examples of non-CNED sets. And in the last couple of minutes, let me just present a slide on the unions of CNED sets. So it's an open question whether the union of two removable closed sets is removable. We can't answer this question now, but we can only answer the question for some trivial cases like unions of disjoint sets. And we only know that unions of Cantor sets and quasi-circles are also removable. So we know how to answer this question in specific cases, but not in general. So what happens with CNED sets? Is the union of two CNED sets CNED? And the answer is yes. If you take a countable collection of closed CNED sets or NED sets, then the union is also CNED or NED. Now, the union doesn't have to be closed. The union can be even dense in Rn. So the answer is yes for CNED sets. But if you drop here this assumption that the sets are closed, then this result is not true anymore. There exist Borel sets which are NED, but their union is not CNED. And actually their union is the product of the Cantor set with 0, 1. Okay, so that's all I had to say. Thank you very much for your attention.
Thank you, Dimitris. Thank you for your nice talk. Are there any questions?
My question would be, so if about your new definition of quasiconformality, so if you compare it with the classical definition using moduli of annuli, how they change, and there is like some uniform constant, how they allowed to change, and your uniform constant which bounds the change of eccentricity. So is there any explicit connection between these constants? And yeah, for example, how would it be, for example, like simple in the setting, simple Weil's lemma look like saying that one quasi-conformal map is conformal?
Yes, so there is a relation. If H is equal to 1, then yes, you get conformality. Now, there is some relation with the K in the classical analytic definition, but it's not, I don't have the explicit formula in my mind right now. It has some, it's related with some powers of K and so on. Let me see. Yeah, first, I mean, one can first look at the relation between the H in the metric definition and the K in the analytic definition. There is here also some explicit relation, which again, I don't remember on top of my head. So, but I think it's related by some exponential. So H is e to the K or something like this. But in the case that one of them is 1, then the other is also 1. So for conformality, the relation is nice, but for other numbers, it's not so nice.
Okay, thank you. Oh, one more question.
Yes.
Sorry. So I wonder, maybe it's a naive question, but for example, in classical settings, there are some conditions when you can check, for example, Beltrami differential, the regularity or conformality at a point is, I wonder, maybe in your setting somehow there are analogous conditions which are maybe simpler, or that you know that your function is differentiable at a point.
So can you repeat again? there are conditions on the Beltrami differential.
Yeah. For example, you want to check, well, you know, the Beltrami differential from, you can integrate it and get a quasi-conformal function. So, but you are interested in whether at some given point, this function would be differentiable.
I see.
Or for example, complex differentiable.
Yes.
Yeah, then you can check some, there are some conditions on the Beltrami differential, you can check them. And so I wonder if we could use your new definition, maybe somehow there is one could come up with with analogous condition, which might be simpler to check, or how you haven't thought in this direction.
Yeah, I haven't thought in this direction, yes. Could it be that in the places where, let's go to I think one should first answer these questions for the classical metric definition before going to the generalized ones. So maybe if this lim sub is 1, maybe you get differentiability at that point. I'm not sure. This would be just a potential result, but I have not thought of the problem.
Okay, yeah. Thank you.
Any other questions?
Yes. I have to. Well, I have a very quick question and then a more serious one. But in your theorem about the removability of your CNED sets,
Yes.
You had a limit. Should I assume this is the lim sup?
Actually, it is an actual limit because the way, let me go on here. The way this is defined, it's as R decreases.
Sorry, yes. So this is the limit anyway. The limit.
So yes, but I think it's easier to read the theorem if you read this equivalent formulation.
This is from your generalized metric definition. So you don't. Okay.
Yes.
So which is, I guess, it's a stronger. Hang on. So there's a weaker condition than
yes.
having the original one.
Yes.
So there's one other class. Well, it's probably more one that I know of. A large class of conformally removable sets, and that's the ones treated by Jeremy Kahn in his PhD thesis, the non-renormalizable quadratic
yes.
Julia sets.
Yes.
So since you were asking, are all holomorphically removable sets a CNED? It's natural to ask, is it clear whether these sets are CNED?
Yes, that's actually a very, very good question, because that work of Jeremy Kahn also provided me some motivation, try to understand his paper in a different way, because the proof that he gave is very ingenious, but I couldn't understand the insights of it. It looked like it's very specific to a dynamical setting. So, but what I believe is true in his case is that the idea in his proof is that there are the good points, which these are the points that can be blown up to top scale. So these are the points where you can get this type of estimate, and then we also have the bad points, which are the point in the little Julia set or in the counter sets in the non-normalizable case. But the bad points are a countable union of NED sets in his case. So if we use the result about the unions of NED sets, then we know that the bad set is also NED. So this is just an alternative way to see his result, but I believe that one can argue like this.
So there should be CNED.
I believe it should be CNED. I haven't really checked the details, but at least from here we can see that the bad set, this is the set that cannot be blown up conformally to top scale, is NED actually, which is stronger.
So that's the kind of non-radial set, the complement of the radial Julia set, I think, if I understand correctly. Anyway, okay.
I would say the preimage of all little Julia sets. Well, they're not connected, but.
Okay, thank you.
Yeah, okay, you're welcome.
Okay, I'm afraid.
So
Yep.
Are we out of time or?
Yes, I think we're out of time, but maybe you can ask over email or something.
Okay, thanks.
Yeah.
Again, thank you very much.
Thank you. So I guess we can start our next talk in 1 or 2 minutes.